Hello and welcome to Foucault's Pendulum for Advanced Experimenters, video number 3. And we are talking decoupling, part B. As you recall, part A was how we developed an inertial frame of reference from a swinging pendulum, and in so that inertia created a decoupling effect. So our bearing surface going in the linear direction, just the swinging direction, is quite simple, and it's just a simple bearing going back and forth. However, in the static and the rotary direction, which is the spin direction, revolving direction, that bearing is more complicated. Now, if you go, I solved the problem if you go back to my two little videos, experiments where I had that swinging pendulum, that small cradle. I used a small magnetic cone coupling to the top, which was just enough magnetism to couple the pendulum without it falling. And the design of that cone at the top was to self-center a bearing in the center of that magnet, which created a universal joint that allowed it to swing in any direction. Now that bearing, although extremely accurate, is not accurate enough for the precision that we'll be going into with the advanced experiments for advanced experimenters. That will require a little bit more knowledge. Now that knowledge I don't believe you'll find anywhere. I have never come across it, not to say that it doesn't exist. And the most important part will be the static bearing. Now that is when the pendulum has actually stopped moving. It has no longer got any inertia. So look, just go quickly to a diagram of our pendulum here. Now, a pendulum basically starts off at a point and it swings to another point. The three most important points on that pendulum swing are this point here, this point here, and this point here. At this point here and this point here, the velocity of the pendulum is zero. It virtually comes to a standstill. At that point, it has no inertia. So it's vulnerable to any parasitic forces, or maybe any force that could cause it to swing off drift. Could be the bearings, or could be the spin of the earth, or whatever. At that point there, it is vulnerable because it has no longer got the inertia which we described in our previous two videos. At this point here, the velocity is maximum. So virtually nothing can influence the swing of the pendulum at that point. It's pretty much on a nothing much can influence it. So its accuracy is very accurate. As we climb up either side, the velocity of the pendulum decreases. So anywhere along this curve here, our vulnerability to drift or error gets greater until this point up here. So basically the mathematics of this is pretty simple. We have two forces, a force going down this way, which is a gravitational force, which is 9.8 metres per second. And we have F2, which is the other force going in this direction, which is a tangential force, combined from this angle from the fulcrum point at the top here. Now, okay, I just made a big mistake. Looking at my board, I've been trying to get this out of my head for 30 years, probably 40 years, probably 60 years. And I've been so brainwashed that I keep writing G as a force. Now we know that G is not a force. Gravity's not a force. So why do I keep writing G? they have brainwashed me so much I can't get out of it. They've done a good job on me. Right, so let's just get rid of that and put pi squared in. A nice Christian number. Let's go back to Christianity numbers. The Creator made this number. Let's go to that. Get rid of that G. Wow. They've done a good job of me. Okay. I'll leave this in the video because I need to vent here. You see what you come across? This is what you have to come across. We have been so brainwashed with all of our science, we can't think clearly. Right. Okay. Where was I? So back to our two forces. Now, the main point here is this actual stopping point. This is really vulnerable at this point here. The pendulum, I tell you now, I've been studying this for quite a while, and this is where the error comes. At that point there, slightest attracted in your bearing will create a chaotic effect. And I can tell you now that from experience, the pendulum will drift left or right. It will go clockwise or anti-clockwise, depending on this variable. And the most critical point is this point here. So now, to explain that further, I have a small experiment which shows you the intricacies of that bearing surface. And I'll go to that now and show you that little video. And it'll be an introduction, and it'll be called the plane pendulum. I had to create my own pendulum, which is a static pendulum, which gives you an idea of the mass of the pendulum, which is not moving. So I'll just switch over that now, and we'll get a good look at that. So here I have the setup to measure my static decoupling bearings. Now, my basic setup, which you'll see in a later video, is a small clock motor driving the hour hand, which drives this toothed cog and a toothed belt assembly, and that gives me the spin of the latitude of the Earth spinning at my latitude, which you'll see clearly in the next video. That'll be video number 4. To test the different, just to show you, with mainly the vulnerability of this pendulum when it has reached its zero velocity point. I have here my plane pendulum, which is a static pendulum, and it weighs 486 grams, which is 5 times heavier than this small brass pendulum. So it has significantly 5 times the inertia as that brass pendulum that you would have seen in those two videos ahead of this. Now, bearing at the moment I have is a needle point bearing. I've been experimenting with different bearings. So the pendulum rests on a bearing surface internally, and to me it's almost frictionless. It's impossible to detect breathing on this thing and it moves. So I've come up with a small gauge, which is pretty rudimentary. It's a piece of wire at a certain length and a certain thickness, and just by pushing on the tip of the wire I can move the pendulum slightly. So there you go, that is the force needed to send the pendulum off centre, which would send it in a clockwise or an anti-clockwise motion. So that's what we're dealing with. Now, just to give you an idea what this force is, I'll have a small weight gauge here. And that force is coming in at, comes in about 0.1 of a gram, 0.1 of a gram, 0.08, 0.09, 0.1. So it comes in at about 0.1 of a gram. That is all that's required. Once this pendulum has stopped moving at that end point, its velocity is 0, that's all it takes to send this off. So that's what we're dealing with. That's what we have to overcome in our bearing accuracy. We can't have any attractant that will give us a chaotic effect. Alright, possibly you may be interested in this as well. Again, you'll see this in much detail in video number 4. But I have experimented with another another bearing surface. This one has a ballpoint pen, so it has a small ball at the end of it. Now I remove the ink and I impregnate it with a fine oil, so it actually has a ball bearing and an oil driven bearing surface. And to be honest, I can't pick the difference between this setup and this setup using this concept here and the wire. However, I have come up, I've just came up with another way to prove this, how to improve the bearing if I have achieved the best bearing possible. And that'll also be shown possibly in the next video, or maybe video number 5. So I think that's enough for the moment. You'll see much more of this detail in video 4. So this was just mostly an introduction to the Pendulum pendulum and its static effect. So okay, thanks for watching, and we'll see you again hopefully in video number 4.